Hey guys, welcome back to my channel. So today let's talk about log transformation. Log transformation is to convert x into a natural logarithm of x, or to convert a unit change in x into a percentage change in x. We're talking about why do we do it, and when do we do it, and how do we do it, okay, and the rationale behind it. So the rationale behind log transformation. In today's video, we're just focusing on linear log model. Okay, without further ado, let's get into it. Log transformation. Here, this log transformation means natural logarithm of x or natural logarithm of y. For example, before I'm interested in the effect of changing x on y. And now I'm interested in changing ln x on y. Let me give you an example. Let's suppose you're interested in the effect of family income on food expenditure. So you have the observation like this subjects n, and then y is the family's food expenditure, how much money you spend on food. You have y sub 1, y sub 2. These are food expenditure for a different family, right? And then x, family income. For each observation, for each family, you have a family income. Suppose they are measured in the unit of a dollar. Then if you run a regression like this, you assume there's a linear relationship between x and y, between income and the family food expenditure. And then the scatter plot look like this, y, x, and they have maybe scatter plot. If you want to use a line, right, a line to describe the relationship between this x and y, you have this regression line. And then is y hat, or y observed value of food expenditure for each family equals y-intercept plus b1 times x, which is family income. And then let me give you this example. I suppose this y equals b0 plus 0.2 times x plus error. And you have this 0.2, and we know that this 0.2 gives us the effect of change in family income on the family's food expenditure. And then you interpret 0.2 as family income increased by $1. Food expenditure, right? The family's food expenditure will increase by 20 cents. Or you can say the family income increased by $1,000 and the food expenditure increased by $200, right? That's how we interpret this 0.2. Unit change in x associated with 0.2 unit change in y. But here, unit is dollars, so x increased by $1 and y increased by $0.2, or x increased by $1,000 and y increased by 1,000 times 0.2, which is $200, right? That's how we interpret this coefficient. It does give us the relationship between x and y, but let's look at whether it makes sense in reality, in the real world. I put this in a real world scenario. So let's suppose this person, before this person earned $200 a year. Just a very hypothetical example. Before this person earned $200 a year. And now this person earned $200 plus $1,000. So that's $1,200 and $1,200 a year. And this is how much change, how much increase in this person or this family's income. Increase from $200 to $1,200. And then based on this relationship, we can say, okay, $1,000 increase in income, increase from $200 to $1,200, and then assuming there's a linear relationship in the family's food expenditure will increase by $200, right? Y is food expenditure increased by this much. Okay, this is one scenario, one person. And for the purpose of comparison, we have another person. The family income before is $1 million. And then after is $1 million plus $1,000. So this is how much change in this family's income. The same thing, $1,000 increase in family income. And then based on this regression, right, this relationship, you can get the same conclusion. It's like the food expenditure for this family will also be increased by $200. right? Because you assume there's a linear relationship. That same amount of increase in X, this is a $200 increase to $1,200, $1,000 increase associated with $200 increase in Y, right? $1,000 increase in X associated with $200 increase in Y. Same thing for $1 million, maybe here, this is $1 million plus 1,000, same amount of increase in X. Supposedly, to use this regression line, you should have the same amount of increase in Y, right? Same amount of increase in Y, which is $200. Right? That's why we say there's a linear relationship. The effect of X on Y is constant, right? For a different value of X. It doesn't matter where you evaluate the value X, the effect of changing X on Y is the same. So apparently, you should compare these two cases, right? One is this $1,000 increase from $200 to $1,200, food expenditure increased by $200, and this person income increased from $1 million to $1 million plus $1,000, and the food expenditure also increased by $200. Apparently, this much increase in food expenditure might not be due to this $1,000 increase in income, because $1,000 compared to this initial family income million is very little, right? So, what make more sense? What would make more sense? Right? How do we model the relationship between family income and food expenditure? So here, people are thinking, okay, maybe the percentage change make more sense. Maybe considering the effect of percentage change in family income on food expenditure make more sense. Okay, so look at how much percentage change for this person's income. For this person's income, how much percentage change? $200 to $1,200 percentage change in X, which is X2 minus X1 divided by X1. That's how we calculate percentage change. Okay, so that's $1,200 minus $200 divided by $200, which equals 1,000, right? On the top and denominator 200, and then you cancel out, you get 5. So we interpret this as a percentage value, which is 500% increase. So the value of X increase from $200 to $1,200 is 500% increase in X. But look at this case. Income increase from $1 million to $1 million $1,000. That will be $1 million plus 1,000 minus $1 million, right? After minus before divided by before. And you have this 1,000 divided by $1 million. And you get this equals 0.001. This equals only 0.1%. That means this much income increase corresponding to only 0.1% increase in family income. So 500% increase in family income versus 0.1% increase in family income. Which one can have a more effect on food expenditure? Apparently this one, right? This 500% increase in family income will have a bigger effect or have greater effect on food expenditure. So now you should understand why sometimes we prefer to use percentage change. Right? We prefer to examine the effect of percentage change in X on Y. Let's look at the percentage change in X on Y. So now I have the same observation. And how Y, food expenditure. And then I have X, which is family income. And now I have ln X, which is log transformation, natural logarithm of X, which is ln X1, ln X2, ln X3, ln X4, and etc. like this. And now instead of run the regression of Y against X, we run a regression of Y against ln of X. So now the regression equation will look like this. B0 plus B1 ln X plus error. Now look at this B1 now. And this B1 gives us the effect on Y of a unit change in ln of X. Right? That's how we get the B1. So that we interpret B1 as ln of X increased by 1 unit. And Y will, for example, the positive B1 is positive, increased by B1 unit. Right? Before we had this unit change in X increased by 1 unit, Y increased by B1 unit. But here is ln x increased by 1 unit. So ln x gave us percentage change in x. So let me write it here. So we want to know percentage change in x, which equals x2 minus x1 divided by x1. After minus before divided by before. And then the numerator is actually change in x divided by x before. So actually this gives us percentage change in x. And now look at ln x, try to find the relationship. How can we use change in ln x to approximate percentage change in x? Okay, again, we're using change in ln x to approximate percentage change in x. Okay, that's kind of the key to appreciate or to understand this linear log model. Okay, we call this linear log regression model. Now let's look at this approximation. So you learn calculus, right? You learn derivative. So you know d ln x, natural logarithm of x. You take the derivative of it, so dx. We call this expression d ln x dx. That's if x increased by 1 unit, how much change in this term, right? So we use derivative because we assume this change is very little. If there's a very little change in x, how much change in ln x? That equals, you have the formula, right? So equals 1 over x. Okay, so now let's make it neater. And now change in ln x, okay, d ln x dx equals 1 over x. And you rearrange this equation. You have this d ln x equals 1 over x times dx. And the d derivative means very little change. So now we can change d into delta. So delta ln x equals 1 over x times delta x, which is change in x over x. You see, if you want to look at a percentage change in x, the two things are the same. A percentage change in x is actually change in ln x. A percentage change in ln x is actually percentage change in x. So now if you want to look at the effect of percentage change in x on y, percentage change in family income on food expenditure, you can just use log transformation. You can interpret this ln of x increased by 1. What does that mean? That means change in ln of x equals 1. And then y increased by b1 unit or units, right? So this we know change in ln of x is here. Right, is here. So we write this as change in x over x is 1. Change in x over x is 1. Think about it. 2 minus 1 over 1 equals 1. So the value increase from 1 to 2 is actually 100% increase. So that's, i.e., x increased by 100%. If x increased by 100%, y will increase by b1 units. Okay, but normally, to make this interpretation more understandable, we will say this, we'll interpret this b1. For example, b1 equals 2. And then we tend to interpret this b1, the value 2, as, okay, interpret this b1 as if x increased by 1%, y is expected to increase by 0.01 times b1 unit. Let me change this to 200. So now I'll just give you an example. So now you can interpret this as, you see, if change in x over x, x increased by 1%, change in x over x is 0.01, which is 1%. And then expected value y will increase by b1 times change in ln x, which is 0.01, equals 0.01 times b1 units. So interpret this B1, this 2, as if family income increased by 1%, 1% increase in family income, the food expenditure is expected to increase by $2. This is how we interpret this B1. And graphically, for this model, graphically, it's like this. Y, X, natural logarithm, right? So this is a 1. So this is y equals b0 plus b1 ln x if b1 is positive. So you see now here you have this, if x increased from $200 to $1,200, and you have the food expenditure increased by this much, right? By this much increase in food expenditure. But if the family income increased from $1 million to $1 million plus 1,000, right? Same amount increase in x, same amount of increase in x, because you're looking at the percentage change, and you have a much smaller increase in y, because increase is just a 0.1% change in x, but this increase is a 500% change in x, associated with the different amount of increase in y. Okay, so this is actually, we use this linear log model to describe a nonlinear relationship. You're assuming that you think the nonlinear relationship make more sense. So that's the effect of x on y, right? The effect of x on y is actually depends on the value of x. Right? The effects of x on y depends on x itself. So the effects of x on y depends on where you evaluate the x. Right? If x from 200 to 1,200, you have this much increase in y. But if x increase from here to here, you have smaller increase in y. So that's why you have nonlinear relationship. So this video is about how to understand log transformation. It's actually to convert unit change into a percentage change. Okay, so to convert a unit change, right, change in x into percentage change in x, or unit change into percentage change. Okay, hope you find today's video helpful, and any questions, comments, concerns, let me know. And as you have seen, this video is focusing on linear log model. You only do log transformation for the variable x, and there are also log linear model, which is ln y equals a function of x, and also log model, which is the regression of ln y, regress ln y against ln x. So there are different ways to model this nonlinear relationship between x and y. So we might talk about that in future videos. Yeah, that's it for today. Any questions, let me know. Thank you so much for watching, and see you next time. Bye.